So in this section 8, we'll consider loop shaping. So the goal is to arrive at a digital controller. So the first method that you can use is digital control emulating analog control, but with loop shaping. So what we'll have is we start from the process. We arrive at an analog controller, and this is using loop shaping. And then we have a given sampling interval, and we obtain a discrete time equivalent description of this controller, and this is C of Z. So remember that this is the first approach, digital control emulating analog design. So of course we have seen in the previous section that what you can do is, and this is then the second approach, you start from the continuous time description in the Laplace domain, and you sample the system, so you obtain a discrete time equivalent description. It is important to take the zero order hold mechanism into account, so this is why we use this zero order hold equivalent description. And then you do the loop shaping, but in the Z domain, and this will produce C of Z, right? And without a surprise, if TS is taking large values with respect to the main time constant, this second approach will be the one to use. Here in this section we'll see that there is a kind of intermediate approach, which is the following one. We'll design a controller using loop shaping for this process here, but we'll take the zero order hold mechanism into account by approximating it by a delay of TS over 2. So this is an approximation of the zero order hold mechanism. So what we'll do is an analog design. So we'll do loop shaping. We'll end up with an analog controller, and then what we can do is sample and obtain a discrete time equivalent description of this controller. So you will see that if you use this digital controller on the original system in the sample data system, this controller will partially take into account the zero order hold mechanism, and you will see that you have results that are intermediate, in the sense that it will be better than this controller, but probably not as good as this design. But for a TS that is not too large, this is also a good way to go. And the advantage is that you can do your design and stay in the analog world and then discretize afterwards. So note that these three controllers will be tested on the original process P of S, where this digital controller is controlling the loop. So this means that there is here a digital to analog conversion with a hold mechanism. So in this case here it's the zero order hold, and here you have an analog to digital conversion. So this is the output. Here you have the reference or set point, and here you have the input or the output of the controller. So these three designs here will be tested on this sampled data system. To explain the loop shaping procedure, you might have to review section 5 and more in particular the subsection on specifications on the Bode diagram. Well, in this subsection, well, we imposed a second order type response of the type and here, well, zeta is the damping ratio and, well, omega n is the natural frequency. And we had seen that in this type of system the settling time is approximately 5 over zeta omega n, right? So this zeta omega n here is the real part of the complex conjugate poles of this system, or the complex conjugate roots of the denominator polynomial. So this is equivalent to imposing that the time constant in closed loop is approximately 1 over zeta omega n. So if you impose that kind of transfer function in closed loop, well, you make the assumption that there is no delay in the system. We had seen that if there is a delay in the system, you could use this rule of thumb, but it's only a rule of thumb and it will work when theta is sufficiently small with respect to the time constants. So usually in a design the maximum overshoot is specified or the desired phase margin is specified. Well, there are some curves in this subsection on specifications on the Bode diagram that allow you to see the relation between overshoot and damping ratio, or phase margin and damping ratio. So in any case, if the overshoot is specified, you know the damping ratio, or if the phase margin is specified, you also have access to this damping ratio. From this damping ratio and this relation over here, you also have now the natural frequency that is fixed, right? There is also a curve that links the normalized crossover frequency to zeta. Okay, the damping ratio, you have the damping ratio, so you have the normalized crossover frequency, so you can obtain the crossover frequency omega c, and you have now all information that you need, right? You have the phase margin and the crossover frequency. If the overshoot has been specified, you know zeta, but since you know zeta, you can also determine then the phase margin. These are the curves I was talking about. So if you're imposing this second order design with complex conjugate poles, then, well, the damping ratio is linked to the phase margin, it is linked to the overshoot, and it is linked to the normalized crossover frequency omega c over omega n. So once you have selected this crossover frequency omega c and this phase margin phi of m, you have to shape the loop gain pc to have this crossover frequency with the selected phase margin, and you have also to select a slope at the crossover frequency. Typically what you do is take a slope of minus 20 dB per decade around the crossover frequency in a frequency range that is a decade or more. You will see in this subsection on specifications on the Bode diagram that there is also a curve that links the slope at the crossover frequency to the damping ratio. So you could go and look in this curve given the damping ratio that you have, but in practice you will see that for, well, normal designs you will always have a slope that is around minus 20 dBs per decade around this crossover frequency. So this is this curve that links the slope at the crossover frequency with the damping ratio zeta, and you can see here that in a practical design you will always have a slope that is around minus 20 dBs per decade. So remember that this is the type of loop gain that you should see in your Bode diagram. So this is here the crossover frequency, the phase margin, and this slope of approximately minus 20 dBs per decade over a frequency range that is larger than a decade. So in the low frequencies, your push to have a high slope, you'll probably have to put an integrator in your loop. This will be good for tracking, well, to reject disturbances, output disturbances, and to be insensitive to variations in the process. And in the high frequencies you want a high roll-off over here, and this is to be insensitive to measurement, noise, and to unmodeled dynamics. Well, the loop gain PC can be shaped while using a controller structure, and this controller structure can be simply a P controller, a PI controller, a PID controller, or a lead lag block. If you're designing a PID controller, design a PI controller first, and if you think that you can improve on the performance, well, add derivative action, and this will allow you then to achieve a better phase margin, right, and possibly push the crossover frequency a little bit further. In this loop shaping procedure, the user has to kind of specify the closed loop time constant, or equivalently the settling time. Okay, settling time and desired closed loop time constant are in a factor of 5. So this tuning factor can be used to speed up or slow down the closed loop response. Increasing the desired closed loop time constant produces a more conservative and less aggressive controller. You will see that this kind of tuning factor is also used in other techniques. You will see in the course of next year, practical process control, that, well, this desired closed loop time constant is also the tuning factor in IMC tuning methods for PID controllers. Well, as a guideline, the closed loop desired time constant is in this interval. So typically it is smaller than the dominant open loop time constant, but it's also larger than the process delay. Well, if you have chosen your closed loop time constant too small, you will see that the loop shaping becomes very difficult, in the sense that it's difficult to have a smooth transition around the crossover frequency over a large frequency range, so typically more than a decade. So if you see that this is becoming difficult or impossible, it's probably because you have chosen this desired closed loop time constant too small. Remember that in the loop shaping procedure you receive a desired closed loop time constant. It could also be a desired settling time, okay, but this is equivalent because there is a factor 5 between those two parameters, and you receive the overshoot, right, and then you can determine omega n zeta, and from zeta you also determine omega c. It could be that in your design you have difficulties in obtaining this smooth transition, right, around the crossover frequency over a sufficiently large frequency range, so typically more than a decade, and this means that you probably have chosen this TCLP here, this parameter, too small. So what you have to do is to redo the design, but with a larger desired closed loop time constant, until, well, you have a design that is satisfactory. So you can see that the resulting procedure becomes iterative. Well, some authors in reference books, in courses, sometimes advocate to compensate an open loop pole of the system, and we have been doing this also in this course for our process, which is 1 over s times ts plus 1. We had used this controller kc ts plus 1 over alpha s plus 1, and you can see here that, well, this open loop pole is cancelled by a 0 of the controller, and this is mostly done because we want to simplify calculations and obtain a simple expression of the loop gain PSCS, right? We'll see in next year's course, practical process control, that this might lead to, well, a poor rejection of load disturbances, and, well, compensating an open loop pole is clearly not always a good idea. So when you do this, you should always remember that in the background this might lead to a bad load disturbance. So I'll try to give you some insights on that. Assume that the process has this pole over here in -1 over ts, so this is the process, and then we have the controller, right? And we'll have also something over here, and we'll be compensating over here. So a load disturbance, and we denote DL or W in the course, will be acting at the input of the system. So you can show, and this will be done next year in the course, that, well, the mode exponential of minus t over the time constant becomes uncontrollable because you have this 0 here in the controller, and this mode, if present in the load disturbance, cannot be controlled, so it will have to disappear naturally from the system, and this might take a while if the time constant is substantial, and therefore this will lead to a poor rejection of this type of load disturbances. What is sometimes done is to do a compensation of an open loop pole for processes of the type PS is Kp over Ts plus 1 to the power n, and let's say, for instance, that n has the value 4 over here, and that a PI controller is used. Remember that this PI controller has the following structure: 1 plus Ti s over Tis. So it's tempting to choose Ti is equal to T, but here this is not really a good idea, because we'll see that in next year's course the integral time constant should be approximately the main time constant of the system, but T here is not the main time constant of the system. So doing such compensations, well, can be done, but only if, well, the pole that is compensated is clearly related to the main time constant. You can see here that this system will not have a main time constant T by looking at the step response. Okay, so So it will look something like this, and it can probably be approximated rather well by a second order system with two main time constants, t1 and t2. So here t1 would be the main time constant and t2 the secondary time constants. So what you have to do in this case, you know it from intuition and from the course of practical process control, is to choose the integral time constant approximately t1, right? But this t1 will in general be much larger than the time constant. So in such a case, well, cancelling one of the poles by a zero of the PI controller is clearly not a good idea, because it will select a PI controller with an integral time constant that is much too small, and it will therefore be very aggressive. So we have seen in the introduction that there is a way to take into account the zero order hold mechanism, at least partially, and this is this third method. Instead of taking PS to design the analog controller, you take PS and you add a delay of the sampling period over 2. Then you do analog design. In our case it's loop shaping, but this is also valid if the control method is not loop shaping, and this will lead to the controller C of S, and then you use, for instance, match poles and zeros to sample and to obtain a discrete time equivalent description of the controller. The idea, of course, here is to obtain a digital controller for the original system P of S. So when you test this controller, it should be in this loop over here. PS, this is a sampled data system. So here we have digital to analog, so in our case a zero order hold mechanism, analog to digital, and then the controller that has been designed over here. So this is how you have then to test this controller. The idea here is that you've taken the zero order hold into account partially. What I see sometimes in the reports of the laboratory assignment associated to this course is that, well, students test this controller with a block that is over here, which is PS exponential of minus TS over 2. This is incorrect. Here we use this process over here only as a vehicle to design this controller while partially taking into account the zero order hold mechanism. The underlying process when you test this controller is of course still PS, right? But of course you have to simulate it, and often this is done in Simulink, taking into account the zero order hold mechanism. If you do it in Matlab, well, then you replace this system by the zero order hold equivalent description of this system. Well, for some control methods it is annoying to have this delay of TS over 2 associated to the transfer function, because the analog design method is not suited to work with delays. And then what you can do is, well, use a Padé approximation, either the zeroth order Padé approximation or the first order Padé approximation. So this leaves us with this second approach of the introduction. You have the process. You do the discretization up front so that you have a zero order halt equivalent description of the system. So this means that you have taken the zero order halt mechanism into account, and then you do loop shaping directly in the Z domain to obtain the digital controller. You can use this bilinear transformation. This is something that has been skipped in the video presentation. You can go and have a look. So the idea is that you work directly in the Bode diagram and shape the loop gain LZ, which is equal to P of Z, C of Z. So if you work directly on the Bode diagram, you can work with PID controllers, and there I advise you to use the discrete time equivalents that we have presented in this course. This is section 6, and for lead lags you can use, for instance, match poles and zeros to discretize and obtain discrete time equivalents. So we'll apply these three methodologies to obtain a loop shaping design on our tutorial process that is given over here, where the time constant is t is equal to 10 seconds. The settling time should be approximately 10 seconds and the overshoot 17%, so we have here that zeta is 0.5. Well, we had already seen that the zeta was the damping ratio 0.5, and well, using this constraint on the settling time, we have this relation over here with a zeta of 0.5. We have a natural frequency in closed loop of 1 radians per second. So if we impose this second order type design with complex conjugate poles, zeta is equal to 0.5, well, yields a phase margin of 52 degrees, right? And you have to go and look in the related curve. We have that omega c over omega n, so the normalized crossover frequency is 0.79. Since the natural frequency is 1, we have now also access to the crossover frequency, and will impose a slope of around minus 20 dBs per decade over a decade at this crossover frequency. Indeed, you can see here that for a value of zeta is equal to 0.5, we have this phase margin that is around 52 degrees. Similarly, for zeta is equal to 0.5, you have this normalized crossover frequency that is around 0.79. So as previously in the previous section, we use a lead lag controller that can be written like this. So this is the gain of the controller, and what we do is parameterize T lead and T lag as follows. Omega c here is equal to 0.79 radians per second, so it's fixed, and Vm was equal to 52 degrees. If you look at this, well, this way of working is kind of centering the lead lag around this frequency c omega c that can be influenced by the parameter c, and if you look at the relation between T lag and T lead, you will see that there is a factor 1 over W, and though this is a parameter you can play with. So what we can do is have a look at the frequency behavior of this lead lag controller. So this is the frequency axis. Here it is again. So this is our frequency C omega C. We'll have it over here also. In here we have a Bode diagram for the gain, and here we'll have it for the phase shift. So if you look at 1 over T lead, this will be CWC over the square root of W. So this is 1 over T lead over here, and here you'll have C omega C times the square root of W, right? So you'll have something similar over here. And what we can now do is have a look at the Bode diagram. So what you'll have here, taking a value of Kc of 1 over here, you'll have here a slope of 20 dBs per decade. That's the presence of the zero. And at 1 over T lag, well, everything becomes constant again. And when you look at it from a point of view of the phase shift, well, you'll have something like this. Okay, so at the frequency C times the crossover frequency, you're lifting the phase and you have the maximum lift. So what you can do is play with the parameter C here to kind of place this frequency where you have the maximum phase lift, and then you can also play with the other parameter W, so that you can play with the width. Okay, so if W is increasing, 1 over T lead and T lag, this frequency range will become larger, and if you make W smaller, this width will decrease. We'll start with parameters C is equal to 1 and W is equal to 10. So this means that the lead lag action is centered at omega C. Omega C here is 0.79 radians per second, and that, well, the frequency range 1 over T lead, 1 over T lag is precisely a decade. Of course, then we have to adapt the parameters C and W in such a way that at omega C is 0.79 radians per second, we have a phase margin of 52 degrees. At this point, this frequency is not yet the crossover frequency. We have to adapt the gain in such a way that this frequency becomes the crossover frequency. An alternative is that you select C and W such that at this frequency the phase margin is 52 degrees, that you look at the root locus and that you, well, select a gain that is such that the corresponding poles go through the line where zeta is equal to 0.5, and this is an alternative way of choosing Kc, well, but you'll end up with the same value of Kc. This procedure is kind of iterative because it will take a while until you have selected the correct values of C and W. Well, this is how you do the design in Matlab. So this is the way to kind of encode the system, which is 1 over S T plus 1, right? And here T is equal to 10. These are the specifications saying that the closed loop time constant is 2 is, well, equivalent to saying that the settling time is 10 seconds, right? This comes from the overshoot that must be 16 and 17%, and from this formula you obtain the natural frequency. Since you know that zeta is 0.5, you know that the phase margin is 52 degrees, and you can also determine the normalized crossover frequency, which must be 0.79, and this results in the crossover frequency. These are the two parameters you can play with. This is this W, and this is the C from the previous slide. And in order to impose 52 degrees phase margin at omega c is equal to 0.79 radians per second, well, W should be 10 and C should be 0.4. So this is the way you kind of introduce your controller, right? Here we take a gain of 1, right? And so this is this controller. Let's write it: T lead S plus 1 over T lag S plus 1. You can see here that T lead, or 1 over T lead, is parameterized by C and this W, and you have something similar with 1 over T lag. So here the loop gain is constructed, so that's P S times CS. Here you obtain a Bode diagram of the loop gain. Here the root locus. This will allow us to check if this one is the correct gain. And here you compute the closed loop system, and you obtain a closed loop step response with the designed controller. So what you see over here is the Bode diagram of the loop gain P times C. So in blue you have this for the original parameters that you see over here, and well, clearly, well, the phase margin is more than this 52 degrees. Also, the transition is not very smooth. So by tuning the controller, and really how this is done is that you first select C and W in such a way that at the frequency omega c is equal to 0.79 radians per second, you have a phase margin of 52 degrees, right? And then you adjust the gain in such a way that, well, this frequency becomes the crossover frequency, and this is indeed the case over here, because here at this frequency you see that the loop gain is 1 or 0 dB. Note that this parameter set ensures that you also have a smooth transition. So here is the associated root locus. So these lines here correspond to zeta is equal to 0.1, 0.2, 0.3, 0.4 and 0.5. We want, well, the roots to be at a point where zeta is equal to 0.5, so we select this or these poles here, and this corresponds to a controller gain of Kc is equal to 1. Well, this is the Bode diagram of the process lead lag and loop gain. So again, we have here that this is the crossover frequency. We have here at this frequency a phase margin of 52 degrees, and we have designed the controller, the lead lag controller, here in such a way that you have a lift of the phase, and we have centered the frequency or the maximum lift at this frequency, which is C omega c, and this corresponds to C approximately 0.4. And by making sure that there is a phase lift over here, we have been able to ensure that at this frequency omega c we have a phase margin of 52 degrees. So this is the closed loop output step response with the initial parameters. C is equal to 1 and W is equal to 10, and then with the tuned lead lag controller using this loop shaping technique, and you can see indeed that we have an overshoot of approximately 17% and that the settling time is around 10 seconds. So what we should do is also look at the control energy, but we have already seen the control energy associated to this closed loop response in the previous section, because you see here that indeed it's exactly the same response, and without a surprise you can kind of see that the controller that is associated with these parameters leads to a controller that is this one over here, and this is exactly the one that we had obtained in the previous section, but with a pole placement approach instead of using here a loop shaping approach. So what we'll do here is use this third method that we've introduced in this section, right? Instead of using P of S, we'll use P of S exponential of minus TS over 2, do an analog design and obtain C of S. In this case it will be loop shaping, and then we'll sample, right, and we'll obtain the discrete time equivalent controller. Okay, so this process only serves as a vehicle to obtain this one. This one again will be tested in a sample data loop on the process P of S. So again what we'll do is use the same controller structure and lead lag, where tail lead and tail lag will be parameterized by these parameters C and W. The interpretation is exactly the same. We'll use this process over here, where this exponential here kind of approximates the zero order hold mechanism. What we'll do is use a TS of 1 second, and this is kind of the same sampling period that we had used in this direct digital control of the previous section. We have now a process with delay. Remember that imposing this second order response with complex conjugate poles was done for a system without delays, and there we had kind of imposed this relation which is exact. But here we have a delay in the system, so what we'll do is use this rule of thumb, and it is to impose that, well, the desired closed loop time constant, which is still 2 seconds, plus the delay, and in this case the delay is TS over 2, is more or less equal to 1 over zeta omega n. This is really a rule of thumb. In a way, this looks like we are kind of changing the desired closed loop time constant, and we making it a little bit higher, okay, and we add, well, the sampling period divided by 2. So if you look at this relation, you have a sampling period of 1 second over here, so this gives you 5 over 2 is equal to 1 over zeta omega n. Zeta is 0.5 since we want an overshoot of more or less 17%, so this yields a natural frequency in closed loop of 0.8 radians per second. Well, we can have a look and link the damping ratio with the phase margin, and link the damping ratio with the normalized crossover frequency. And if you look in the curves, you will see that the normalized crossover frequency for zeta is 0.5, is 0.79. You multiply by the natural frequency and you obtain the new crossover frequency for this design with additional delay. So this is the frequency at which we'll have to impose a phase margin of 52 degrees, and of course around this crossover frequency will impose a slope of around minus 20 dBs per decade. We'll start from the previous design and we'll play with the parameters C, W and Kc until we meet the specifications that we have imposed in this slide. So here we have defined the Laplace variable, and in this way it is easier to encode the system with this additional delay of Ts/2. So these are the specifications. So this is imposing that TCLP plus, in this case, theta, which is half the sampling period, is, well, approximately 1 over zeta omega n, right? And from zeta you obtain the natural frequency. So with this zeta you obtain the phase margin, but also the normalized crossover frequency, and therefore you obtain the crossover frequency, right? So now you can start playing with the parameters W and C to encode your controller with a certain gain, and then you can have a look at the loop gain here, L of S. This is P times C, and then you can have a look at the closed loop transfer function and, well, look at a step response. This is the step response with this system over here, and this closed loop is interesting only to see if our controller C of S is meeting the specifications that we have imposed. So here you're looking at the loop gain L of S, which is P times C for the original controller, and that's the one coming from the original design without taking into account Ts/2, and for the new design. So you can have a look at here the crossover frequency, and this corresponds more or less to what we had specified, that the crossover frequency had to be 0.63 radians per second, and if you look at the phase margin you obtain here 52 degrees. So this is the closed loop response. It's our analog design C of S, right, on the process with this, well, delay of Ts/2, and this is just to have a look at the closed loop response to see if we meet the specifications. And here we see that we have a overshoot of roughly 17%, and we have a settling time of roughly 10 seconds over here. So we meet the specifications, but apart from that, this closed loop step response has no use. So in the end, these are the parameters that we have obtained. If you plug that into the controller, remember that tail lead and tail lag are functions of C and W. This is what you obtain. Okay, so we'll call this C2 of S, and if you compare this with C1, of S, then you had a gain of 1, a tail lead of 10, and a tail lag of 1. Of course, this controller and this controller are not the ones we are interested in. We're looking for a digital controller, and these controllers will result from the discretization of these two controllers using the matched pole and zero approximation method. So what we'll do right now is obtain C1Z, C2Z, and we'll look at the closed loop behavior. Taking into account the zero order hold mechanism. So you can do this, for instance, in Matlab, and this is what we'll do, is take here the zero order hold equivalent description of the process and then plug in these controllers and see what happens. The alternative is to do it in Simulink, and then you have to use this zero order hold mechanism, this rate transition, as we have showed before. As a reminder, this is the zero order hold, and this is really the zero order hold equivalent description of the system that we had found previously. So what we have done here is obtain the discrete time equivalence of the controller C1S and C2S using the mapped zero pole method. So the idea is that you start from C of S is equal to KC tail lead S plus 1, tail lag S plus 1. This will lead to a C of Z where you have a gain over here. We'll come back to that later, and we'll have a 0 at minus TS over tail lead and a pole at exponential of minus TS over tail lag. And what is then done is that, well, this one is adjusted in such a way that the two controllers have the same static gain. If you do this for the original design, okay, the original design based on the process without a delay, this is the discrete time controller that you obtain. And if you do this on the new design, right, with the process with the additional delay of TS over 2, you'll end up with this discrete time description of the controller. So using this Matlab code, we can actually test the two controllers on the zero order hold equivalent of the original system. So notice in this case we use the original system without the delay, and we compute its zero order hold equivalent description. So this is the design here, C of S, where we take into account the delay of TS over 2. You can see it over here. Remember that this is as if we're taking another desired closed loop time constant where we add half of the sampling period. So this will produce C of S, and of course to test our controller we have to compute the corresponding digital controller, and for that we use the match pole 0 method using the command C2D. So we are now in a position to test our digital controller on the discrete time zero order equivalent of the system. So what we can have a look at is the loop gain. If necessary, you can have a look at the root locus. As I've said, it can be used to obtain the gain. It's one of the methods, and then you can compute the closed loop system and obtain the closed loop response at the sampling instance. This is what you can obtain in Matlab. If you would do the check in Simulink, you would have to use this controller here and, well, obtain a simulation where you have the original system that you precede by a zero order hold mechanism, and where you have after the process a rate transition. And the advantage would be that you would be able to test also the inter-sample behavior. So here you see the output closed loop step response. The energy of control is not shown, but in reality you should do this also. And in blue you see the original matched design that we have now applied on the original system with a TS of 1 second. Okay, and what you see here is the response that we have seen in the previous section. Well, since we have not taken into account the zero order hold mechanism, well, the specifications are not met. This delay that has not been taken into account will make sure that the phase margin is much smaller as expected, and therefore you have a lot of overshoot, right? You can see that this matched design, but for the process with delay, does a lot better. You can see that the specifications are not met exactly, because you would expect here something around 16 to 17%, but as we have taken the zero order hold mechanism partially into account using this delay of TS over 2, you can kind of see that this digital controller C2 of Z does a rather good job to control the original system P of S with this sampling period of 1 second. So we can see that the C2 of Z, based on this match design on the original process with an additional delay of TS over 2, yields a much better result. And this is because, as I've said, the zero order hold mechanism has been partially taken into account using this delay of TS over 2. And this type of design, this is this third method that we had introduced in the introduction. Well, it will work as long as the sampling period TS is not too large when compared with the main time constant of the process. So in this subsection we do the design directly in the digital world. We do the loop shaping based on a discrete time Bode diagram. So for that we need a description of the process that takes into account the zero order hold mechanism, and what we'll do is we'll use our continuous time controller structure and transform it to a digital controller using the matched poles and zeros method. For this direct digital design, we have to find the crossover frequency and the phase margin. We'll proceed as we have done with this design that takes the process and adds a delay of TS over 2. So the settling time defines the closed loop time constant, the overshoot the zeta, and we'll use this rule of thumb method that says that the closed loop time constant with the delay, in this case TS over 2, is approximately equal to 1 over zeta omega n. If you look at this relation in this case here, with zeta is equal to 0.5, this yields a natural frequency of 0.8. The zeta of 0.5 will give you a phase margin of 52 degrees, a normalized crossover of 0.79, and so we'll have a crossover frequency at 0.63 radian per second. So that's the frequency at which we have to impose this phase margin of 52 degrees. Of course, around the crossover frequency we have to impose a slope of minus 20 dBs per decade, and as usual we'll start from the previous design. Well, this Matlab file for direct digital design looks a lot like the one that we had for digital implementation. So what we need is the zero order hold equivalent description of the process. Here you have the design, right? So this defines C of S. Here we have the match pole, match zero approximation of this analog controller. So we have the digital controller. Here we have our description of the process that takes into account the zero order hold mechanism, and what we'll do is play with the parameters C and W, but we'll look directly at the loop gain L of Z in the Z domain, right? And we'll impose a phase margin of 52 degrees at this crossover frequency of around 0.63 radians per second, right? The difference is that we now look here at the loop gain in the Z domain. Once we have obtained the correct parameters, and in this case for this direct digital design it's W25, C 0.75 and a gain KC of 0.63, what we can do is compute the closed loop system and obtain the closed loop step response at the sampling instance. Here we evaluate in Matlab. As I've said many times, you can do this also in Simulink with the advantage that you have also the intersample behavior. So here what you see is the loop gain, but in the Z domain. So P times C, you can clearly see it's in the Z domain because here we have the Nyquist frequency, which is pi as TS is equal to 1 second. So you see the three designs, and in the direct digital design, well, we impose here a cutoff frequency of omega C is equal to 0.63 radians per second. You can see it's a crossover frequency because the gain is 1 or 0 dB, and at that, well, it's a bit further, at that frequency you can see that we impose here a phase margin of 52 degrees, and you can see here that the previous two designs are a bit off. This one, well, it's really different, but you can see here that the matched design on the system with delay comes relatively close. So here you have the output closed loop responses for the three designs. Remember that the sampling period is 1 second over here, and clearly you can see that the specifications are met exactly only for the direct digital design, so 17% here and a settling time of 10 seconds. But you see that the match design on system with delay comes very close. So with this direct digital design we arrive at parameters that are given over here, and if we plug them in into the structure and, well, apply this match pole match zero algorithm for approximation. This is the discrete time or digital controller that we obtain, and as you have seen, it achieves slightly better results than the one based on a matched design, but that takes into account the additional delay of TS/2.